Welcome, weary traveller of the cosmos. As you settle in for a journey through the dimensions, take a moment to get comfortable and let your mind drift. Whether you're just winding down for the day or already nestled snug in your bed, I'm glad you've chosen to explore these mind-bending mysteries with me tonight. Before we dive in, I'd love to know where in the world you're tuning in from and what time of day it is in your corner of the universe. Are you watching the sunset paint the sky in pastel hues, or counting the stars as they slowly emerge in the inky depths of night? Feel free to say hello and let me know in the comments below. And if you enjoy pondering the profound mysteries of science and history as much as I do, go ahead and click that subscribe button so you can come along on future adventures. But for now, let the soothing whisper of science draw you in as we embark on a journey far beyond the familiar three dimensions of our everyday world. Take a deep breath, let your eyes grow heavy, and let's set sail for the strange seas of hyperspace and parallel universes that may lie hidden all around us. As we gaze up at the vast expanse of the night sky, it's easy to feel small and insignificant in comparison to the sheer scale of the cosmos. The stars seem to go on forever, stretching out to infinity in every direction. But as we ponder the billions of glittering points of light, we start to wonder, is there more to this universe than meets the eye? Might there be hidden dimensions beyond length, width, and depth? Entire realms of reality that our senses can't perceive? These questions have captivated great thinkers for thousands of years. In the days of ancient Greece, when natural philosophy was just beginning to part ways with mythology, scholars looked to the clockwork motions of the heavens for clues about the structure of creation. The Greek astronomer Ptolemy, building on ideas from Aristotle and Eudoxus, proposed that the sun, moon, planets and stars were embedded in nested crystalline spheres that rotated around the Earth. To the ancients, what we now know to be the three dimensions of space were imagined as great cosmic onion layers, with the Earth cradled in the centre. Ptolemy's cosmology may seem quaint to us now, but it was a remarkably sophisticated model for its time, with circles upon circles used to predict the wandering motions of the planets against the fixed backdrop of stars. For over 1,000 years, Ptolemy's ideas would remain central to astronomical thought in the Western world. And while we've long since abandoned the notion of celestial spheres, the ancient fascination with otherworldly geometry planted the seeds for modern speculations about higher dimensions. As the centuries rolled by, new discoveries in mathematics and physics began to paint a very different picture of the universe. In the 1600s, the English polymath Isaac Newton unlocked the secrets of motion and gravity, showing how the same elegant laws could describe the arc of a cannonball and the orbit of the moon. Newton envisioned space as an unchanging three-dimensional grid, with time flowing steadily from past to future like a river. In Newton's universe, the basic building blocks of reality were imagined to be solid, massy particles, chunky corpuscles of matter blindly obeying the strict commandments of physics. But in the early 1700s, the mathematician Leonhard Euler began to stretch Newton's conception of space. Euler was fascinated by the geometry of higher dimensions, and he developed a systematic way to describe spaces with any number of dimensions using coordinates. In a three-dimensional space, you can locate any point by specifying its position along three perpendicular axes: length, width, and height. But Euler realized there was no reason to stop at three. His equations could describe spaces with 4, 5, 6, or any number of dimensions, each one spanning out at right angles to the others. At the time, higher dimensional spaces were seen as mere mathematical curiosities, with no obvious connection to the real world. Scientists assumed that the universe was fundamentally three-dimensional, and that higher dimensions were just abstract fancies, useful for solving certain technical problems but with no physical meaning. In the 1700s, the Scottish mathematician and theologian Colin Maclaurin even used the absurdity of higher spatial dimensions as an argument against the existence of a fourth dimension of time, which he saw as theologically unacceptable. But in the late 1800s, new geometric insights began to emerge that would pave the way for higher dimensions to be taken seriously as scientific possibilities. The German mathematician Bernhard Riemann, expanding on earlier work by Carl Gauss, showed how to describe curved spaces with any number of dimensions using a mathematical framework called Riemannian geometry. In Riemann's approach, the familiar flat geometry of everyday life is just a special case, a flat slice through an infinite array of possible curved spaces. Riemann's ideas would find their most spectacular application in the hands of Albert Einstein, who realized that gravity could be reimagined as the curvature of four-dimensional space-time. In Einstein's general theory of relativity, massive objects like stars and planets create dimples and ripples in the cosmic fabric, and free-falling objects simply follow the straightest possible paths along the contours of curved space-time. Suddenly, time was no longer separate from space. The two were intimately interlinked, with the future and the past relative to the observer's motion. Einstein's unification of space and time into a four-dimensional continuum sent shockwaves through the physics community. The stately Newtonian universe of absolute space and time had been overthrown, replaced by a mind-bending cosmos where distances stretch and shrink, and time itself runs faster or slower, depending on your frame of reference. Physicists scrambled to explore the implications of Einstein's equations, which opened up a Pandora's box of cosmic oddities. One of the strangest possibilities to emerge from Einstein's equations was the existence of black holes. First proposed by the German physicist Karl Schwarzschild in 1916, black holes were imagined to be regions of space where matter had collapsed in on itself, creating a gravitational field so strong that not even light could escape. At the center of a black hole, Einstein's equations predicted a singularity, a point where space-time curved in on itself so tightly that the laws of physics simply broke down. For decades, physicists debated whether singularities were mere mathematical artifacts or real features of the universe. But as observational evidence for black holes began to mount in the 1960s and 70s, scientists were forced to grapple with the unsettling possibility that our universe contains ruptures in the very fabric of space-time. Some even began to speculate that singularities might be portals to other dimensions, wormholes that could theoretically allow passage to otherwise unreachable realms. As the 20th century progressed, the quest to understand the fundamental building blocks of nature drove physicists to probe ever smaller scales of reality. By smashing particles together at higher and higher energies, researchers discovered a bewildering zoo of subatomic entities, quarks, leptons, and bosons obeying the strange rules of quantum mechanics. But as the standard model of particle physics took shape, physicists began to suspect that its menagerie of particles might be a mere shadow of a deeper, more symmetric reality. In the 1920s, the German physicists Theodor Kaluza and Oskar Klein proposed a bold new way to unify Einstein's theory of gravity with James Clerk Maxwell's theory of electromagnetism. Kaluza and Klein suggested that the two forces could be elegantly combined if the universe had an extra spatial dimension, curled up into a tiny circle too small for humans to perceive. In their theory, ripples in the fabric of five-dimensional space-time gave rise to both gravity and electromagnetism, with the hidden extra dimension providing the key to their unification. The Kaluza-Klein model was ultimately abandoned as a realistic description of nature, but it planted the seed for the idea that extra dimensions could help simplify the laws of physics. In the 1960s and 70s, physicists began to explore new theories that used extra dimensions to unify the fundamental forces. These grand unified theories, or GUTS, imagined that at extremely high energies, the strong nuclear force, weak nuclear force, and electromagnetic force would merge into a single unified force, with the symmetry between them broken at lower energies by the curling up of extra spatial dimensions. But physicists soon realized that even GUTS were incomplete. To truly unify all of nature's forces, including gravity, they would need a quantum theory of gravity, a way to describe the jittery, probabilistic behavior of space-time itself at the smallest scales. This proved to be an enormously difficult problem, with Einstein's smooth, continuous conception of space-time stubbornly refusing to play nice with the discrete, jumpy world of quantum mechanics. In the 1980s, a new approach emerged that seemed to offer a way forward. Called string theory, it proposed that all particles and forces arise from the vibrations of tiny, one-dimensional strings of energy, wiggling and oscillating in a space with 10 or even 26 dimensions. The math was mind-meltingly complex, but it offered a tantalizing glimpse of a theory of everything that could unify all of nature's forces and particles into a single harmonious framework. As string theory matured, it sprouted new branches and offshoots. In the 1990s, theorists discovered that the 5 different versions of string theory were actually limiting cases of a more fundamental 11-dimensional theory called M-theory. New concepts like brains, multi-dimensional membranes that could act like particle-absorbing walls, and dualities, mathematical mappings that could relate seemingly different string theories, hinted at a labyrinthine network of interconnected ideas, all pointing towards a profound new understanding of the universe. But despite its mathematical beauty, string theory and its descendants remained frustratingly untethered from reality. The extra dimensions they required were too small to observe directly, and the energies needed to probe them lay far beyond the reach of any foreseeable particle accelerator. Critics charged that string theory was more mathematical philosophy than testable science, with its vast landscape of possible universes untethered from experimental evidence. Nonetheless, the siren song of extra dimensions continued to call to physicists. Some theorists proposed that extra dimensions could be probed indirectly, through subtle effects on the behavior of particles or the ripples of gravitational waves. Others looked for signs that extra dimensions could explain long-standing puzzles like the hierarchy problem, the vast, seemingly unnatural difference in strength between gravity and the other forces of nature. Meanwhile, observational cosmologists began to explore the possibility that our universe is just one bubble among many in a vast multiverse, an infinite froth of parallel universes, each with its own unique laws of physics and roster of spatial dimensions. Some versions of string theory predict a staggering number of possible universes, perhaps 10 to the power of 500 or more, with each corresponding to a different way of curling up the extra dimensions. If the multiverse is real, it could help explain why our universe seems so uncannily fine-tuned for the emergence of complex structure and life. With an infinite number of universes to choose from, maybe it's not so surprising that we find ourselves in one with just the right laws and constants to allow stars, galaxies, planets, and ultimately us to exist. But the multiverse hypothesis remains controversial, with some physicists seeing it as an untestable cop-out and others embracing it as a natural consequence of inflation. The theory that the early universe underwent a period of rapid, exponential expansion. As we ponder these dizzying vistas of higher dimensions and parallel universes, it's natural to wonder what these hidden realms might actually look like. How can we visualize spaces beyond the familiar 3 dimensions of our everyday experience? One way is to start with the lower dimensional worlds and work our way up. Imagine a universe that consists of a single line, stretching off to infinity in either direction. Beings in this one-dimensional world would only know forward and backward. There is no left or right, up or down. Their entire existence would be constrained to a single axis. Now picture a 2-dimensional universe, an infinite flat plane like a sheet of paper. Flatlanders in this cosmos would experience length and width, but no height. They could move forward and backward, left and right, but the 3rd dimension would be as incomprehensible to them as the 4th dimension is to us. If a 3-dimensional object like a sphere were to pass through the Flatlanders' 2-dimensional world, they wouldn't perceive it as a sphere. Instead, they would see a mysterious circle that appears out of nowhere, grows to a maximum size, then shrinks and vanishes as the sphere moves through their plane. The sphere's cross-section is all they could directly observe. Its extension into the 3rd dimension would be unseeable and unknowable to them. By analogy, a 4D object passing through our 3D universe would appear to us like a ghostly apparition, materializing out of the ether, its form morphing in seemingly impossible ways as more and more of its bulk slides into our world, then dwindling away into nothingness as it moves beyond our perceptual horizon. A 4D being would be able to see our entire timeline laid out before them, past, present and future, coexisting as part of a single 4D shape. They could even reach into our world and pluck us out, like a flatlander lifting a 2D creature out of its plane. To get a sense of what a 4D object might look like, We can start with a familiar 3D shape and add an extra dimension. Take a cube, for example. A cube has 6 square faces, 12 edges, and 8 vertices. Its 4D analogue is called a tesseract or hypercube, first described by the mathematician Charles Hinton in the late 1800s. A tesseract can be thought of as a cube within a cube, connected by diagonal lines. It has 8 cubical cells, 24 square faces, 32 edges, and 16 vertices. As it rotates in 4D space, its 3D cross-sections twist and turn in mind-bending ways, with cubes appearing to merge and split, their faces opening up like petals to reveal new cubes within. Visualizing a tesseract is a bit like trying to picture a Mobius strip or Klein bottle. Our brains struggle to fully wrap themselves around the alien geometry. But just as two-dimensional creatures could infer the existence of the third dimension by studying the strange behavior of three-dimensional objects passing through their world, we can use mathematical reasoning and analogies to get a sense of what higher dimensional objects might be like. As the 20th century drew to a close, physicists continued to explore new ways to probe the possibility of extra dimensions. Some theorists proposed that extra dimensions could have measurable effects on the behavior of subatomic particles. At high enough energies, particles might be able to jump into the extra dimensions, causing apparent violations of conservation laws, or producing missing energy that could be detected in particle colliders. Other scientists looked for signs of extra dimensions in the ripples of gravitational waves, tiny disturbances in the fabric of space-time predicted by Einstein's theory of general relativity. If extra dimensions exist, they could subtly alter the way gravitational waves propagate through space, leaving telltale patterns in the data collected by gravitational wave observatories like LIGO and Virgo. Some theorists have even proposed that our entire universe is a hologram, a lower dimensional projection of fundamental physics unfolding in a higher dimensional space. According to this idea, the apparent smoothness of space-time is an illusion, emerging from the complex interplay of quantum bits of information encoded on a distant boundary. Like a 3D image popping out of a 2D hologram, our universe may be a shadow of a more fundamental reality beyond our perceptual horizon. Perhaps the most tantalizing possibility is that black holes could act as portals to other universes. Some versions of string theory suggest that the singularities at the centers of black holes are actually cosmic doorways, leading to entire new universes budding off from our own. If this is true, then every black hole may be a gateway to an infinite multiverse, a churning sea of parallel realities, each dancing to the beat of its own higher dimensional drum. As we contemplate these vertiginous vistas of hyperspace and alternate dimensions, it's hard not to feel a sense of awe and humility. The universe we inhabit may be but a single facet of an infinitely greater whole, a cosmic jewel glittering in the darkness of a higher dimensional void. Through the lens of science and mathematics, we are slowly peeling back the layers of reality, groping our way towards a deeper understanding of the true nature of existence. But even as we push the boundaries of human knowledge, we must remember that we are still in the early days of this grand cosmic odyssey. The universe is vast and strange, and our efforts to unlock its secrets have only just begun. It may be that the nature of higher dimensions will forever elude our understanding, lost in the mists of an ultimately unknowable reality. And yet the journey itself is worth more than the destination. By daring to ask these deep questions, to venture out into the uncharted waters of the imagination, we affirm our place in the cosmos as curious, questing beings, forever seeking to expand the horizons of the possible. Each new theory, each fresh insight, is a small candle lit against the encroaching darkness, a glimmer of understanding in the face of the unknown. So as we drift off to sleep, our minds reeling with the strange and beautiful possibilities of higher dimensions, let us embrace the mystery and wonder of it all. The universe may be stranger and more complex than we can ever truly fathom, but that only makes the pursuit of knowledge all the more thrilling and vital. In our dreams, let us wander through the twisted geometries of Riemann and Einstein, plumb the inky depths of Schwarzschild's singularities, and surf the quantum foam of Kaluza and Klein's filigree dimensions. Let us be like as we continue our exploration of the strange and wondrous possibilities that other dimensions hold, let us turn our attention to the visionaries who dared to dream beyond the confines of our everyday experience. One such figure was the brilliant mathematician Georg Bernhard Riemann. Born in 1826 in the Kingdom of Hanover, now part of Germany, Riemann showed an early aptitude for mathematics, devouring complex texts as a young student. In 1854, he delivered a groundbreaking lecture at the University of Göttingen that would forever change the way we think about geometry and higher dimensions. In his talk, titled "On the Hypotheses Which Lie at the Basis of Geometry," Riemann proposed a radically new way of understanding space. He suggested that the geometric properties of a space were not fixed and absolute, but could vary depending on the space's curvature. This idea of curved space would later become a cornerstone of Einstein's general relativity. But Riemann didn't stop there. He also introduced the concept of n-dimensional manifolds, mathematical spaces that locally resemble Euclidean space near each point. An n-dimensional manifold has n coordinates, allowing it to describe spaces with any number of dimensions. Riemann's insights opened up a dizzying new realm of geometric possibilities, from the four-dimensional spacetime of relativity to the 10-dimensional arenas of string theory. Sadly, Riemann struggled with poor health throughout his life, contracting tuberculosis at a young age. He passed away in 1866 at the age of 39, leaving behind a legacy that would inspire generations of mathematicians and physicists. His ideas about higher dimensions and curved space would pave the way for Einstein's revolution and forever change our conception of the cosmos. As the 19th century gave way to the 20th, another visionary stepped onto the stage, the Dutch physicist Hendrik Lorentz. Born in 1853 in the town of Arnhem, Lorentz showed an early passion for physics and mathematics. In 1875, he completed his doctorate at the University of Leiden with a thesis on the reflection and refraction of light. But it was Lorentz's work on the behaviour of electric and magnetic fields in moving frames of reference that would cement his place in scientific history. In the early 1890s, he began developing a theory to explain the puzzling results of experiments by physicists like Albert Michelson and Edward Morley, who had tried and failed to detect the Earth's motion through the luminiferous ether that was believed to permeate space. Lorentz proposed that objects moving through the ether would contract in the direction of motion, and that time would slow down for moving clocks. His transformations provided a mathematical framework for relating measurements in different inertial reference frames. But Lorentz still clung to the idea of an absolute ether, a universal resting frame. It would take the genius of Albert Einstein to reinterpret Lorentz's transformations and arrive at the revolutionary insight that space and time were relative, that the speed of light was constant for all observers, and that there was no need for a luminiferous ether. Einstein's special theory of relativity, published in 1905, would overthrow the Newtonian conception of absolute space and time that had reigned for centuries. Lorentz and Einstein would maintain a friendly rivalry and mutual admiration throughout their lives. Though Lorentz never fully embraced the radical consequences of relativity, he praised Einstein's theory as a monument of science, and even proposed Einstein for the Nobel Prize. Lorentz passed away in 1928, having lived to see the quantum revolution that he helped to spark with his early work on electromagnetic theory. As we lay here in the dark, our minds drifting on the currents of history, we can only marvel at the courage and creativity of thinkers like Riemann and Lorentz. Their willingness to question established ideas and venture into uncharted intellectual territory made possible the revolutions of relativity and quantum mechanics that shape our understanding of the cosmos to this day. And yet, even as we celebrate these triumphs of human imagination, we must acknowledge that they represent but tiny steps in an infinitely vast journey of discovery. With each passing generation, new pioneers take up the torch, probing ever deeper into the mysteries of the universe and the mind-bending possibilities of higher dimensions. Today, physicists and mathematicians continue to explore the strange and wonderful landscape that Riemann and Lorentz helped to unveil. From the elegant geometries of Calabi-Yau manifolds to the dizzying symphonies of string theory, from the holographic conjurings of AD-CFT correspondence to the reality-warping tangles of quantum entanglement, the frontiers of knowledge beckon to us with whispers of dimensions beyond our ken. As we drift off to sleep, let us dream of these hidden realms and the intrepid explorers who seek to chart their contours. Perhaps, in some distant era, our descendants will venture forth into the extra dimensions, sailing through seas of possibility undreamt of by their forebears. And as they do, they will carry with them the legacy of all the brilliant and courageous thinkers who dared to imagine the unimaginable and to seek the unseeable. But for now, let us rest, content in the knowledge that we are part of an ancient and ongoing quest to unravel the deepest secrets of the cosmos. May our dreams be filled with visions of hypercubes and hyperspheres, of Riemann zeta functions and Lorentzian wormholes, and may we awaken with renewed wonder at the majesty of the universe and the boundless power of the human mind to fathom its mysteries. Good night, brave traveller, and pleasant dreams of the dimensions that lie beyond the veil. As we ponder the possibilities of extra dimensions, it's worth noting that these ideas are not just the province of modern physics. Throughout history, philosophers and mystics have also speculated about the existence of higher planes of reality. In ancient Greece, Plato proposed his famous allegory of the cave, in which prisoners are trapped in a dark cavern, seeing only the shadows of objects cast by a fire behind them. For Plato, this represented the limited nature of human perception. We see only a pale reflection of the true forms that exist in a higher realm of ideas. This concept of a world beyond the physical would influence Western thought for centuries to come. In the East, the Hindu and Buddhist traditions have long embraced the idea of multiple dimensions of existence. The Hindu cosmology describes a vast multiverse of countless worlds, each with its own cycle of creation and destruction. Some of these planes are said to be inhabited by devas, or celestial beings, who exist in a state of pure consciousness beyond the limitations of physical form. Similarly, Buddhist texts speak of different realms of rebirth, from the hell realms of suffering to the God realms of bliss. The ultimate goal of the Buddhist path is to transcend all of these planes and attain nirvana, a state of perfect peace and freedom beyond the cycle of death and rebirth. In the Islamic tradition, the Quran describes 7 heavens, each more magnificent than the last, leading up to the throne of Allah. The Jewish mystical tradition of Kabbalah also speaks of multiple levels of reality, represented by the Tree of Life diagram with its 10 interconnected spheres. These spiritual visions of higher dimensions may seem far removed from the mathematical models of modern physics, but they share a common thread: the idea that there is more to reality than meets the eye. Whether we conceive of them as spiritual planes or as extra-spatial dimensions, these hidden realms beckon us to expand our horizons and consider the mysteries that lie beyond our everyday experience. As we explore these ideas, it's important to remember that science is an ever-evolving quest for knowledge, not a fixed set of dogmas. The theories of extra dimensions are still just that: theories waiting to be confirmed or refuted by experimental evidence. But even if they prove to be wrong, they will have served a valuable purpose by stretching our imaginations and pushing us to ask deeper questions about the nature of reality. One of the most mind-bending aspects of extra dimensions is the way they challenge our common-sense notions of space and time. In our everyday experience, space seems to have 3 dimensions: length, width, and height, while time flows in a linear fashion from past to future. But as we've seen, Einstein's theory of relativity shows that space and time are actually intertwined, forming a 4-dimensional continuum called space-time. This means that the distinction between space and time is not as clear-cut as we might think. In fact, physicists have shown that a fast-moving object will actually experience time more slowly than a stationary one, a phenomenon known as time dilation. This effect has been measured with atomic clocks flown on airplanes, and it even needs to be taken into account in the GPS satellites that guide our devices. But if extra dimensions exist, the nature of space-time becomes even stranger. In some models, the extra dimensions are compactified, curled up into tiny loops or knots at every point in space. If this is true, then there could be entire universes hidden within the fabric of our own, just beyond our perception. Other theories suggest that our universe is just one of many brains, 3-dimensional membranes floating in a higher dimensional space called the bulk. In this scenario, gravity is the only force that can leak out of our brain into the bulk, which could explain why it appears to be so much weaker than the other fundamental forces. These ideas may sound like science fiction, but they are grounded in rigorous mathematical models and could have profound implications for our understanding of the cosmos. If extra dimensions exist, they could help to explain some of the deepest mysteries in physics, from the nature of dark matter and dark energy to the origin of the universe itself. Of course, finding evidence of extra dimensions is no easy feat. By definition, they would be invisible to our current instruments, which are designed to detect objects in three-dimensional space. But physicists are nothing if not resourceful, and they have devised a number of clever ways to search for signs of hidden dimensions. One approach is to look for tiny deviations in the strength of gravity at very small scales. If extra dimensions are curled up into tiny loops, they should cause gravity to behave differently at distances comparable to the size of the loops. Physicists have conducted experiments using torsion balances and other sensitive instruments to look for these deviations, but so far have found no evidence of extra dimensions down to scales of less than a millimetre. Another way to search for extra dimensions is to look for their effects on the behaviour of subatomic particles. In some models, extra dimensions could allow particles to take shortcuts through the higher dimensional space, changing the way they interact with each other. The Large Hadron Collider at CERN, the world's most powerful particle accelerator, has been searching for signs of these extra dimensional effects, but has yet to find any conclusive evidence. Perhaps the most exciting possibility is that extra dimensions could be detected through their effects on the cosmic microwave background, the faint afterglow of the Big Bang that fills the universe. If extra dimensions exist, they should have left their imprint on this ancient light, causing subtle variations in its temperature and polarization. Experiments like the Planck satellite have been studying the cosmic microwave background with unprecedented precision and could potentially uncover signs of extra dimensions in the coming years. As we lie in bed, our minds drifting on the edge of sleep, it's easy to feel overwhelmed by the sheer scale and complexity of these ideas. The thought of extra dimensions, hidden universes, and the vast expanses of space and time can make our own lives feel small and insignificant in comparison. But in a way, that's exactly the point. The study of physics and cosmology is not just about uncovering the secrets of the universe, it's about understanding our place within it. By pushing the boundaries of our knowledge and exploring the frontiers of the possible, we are not diminishing ourselves, but rather expanding our sense of wonder and awe at the incredible richness and diversity of the cosmos. And who knows, perhaps one day, far in the future, our descendants will have unlocked the secrets of extra dimensions and learned to navigate the higher realms of reality. Perhaps they will look back on our time as a primitive era, when we were just beginning to glimpse the true nature of the universe. Or perhaps they will marvel at the ingenuity and determination of the scientists and thinkers who dared to dream of worlds beyond our own, even in the face of daunting odds and technological limitations. For now, all we can do is keep exploring, keep asking questions, and keep pushing the boundaries of the known. Whether or not extra dimensions turn out to be real, the search for them has already enriched our understanding of the universe and our place within it. And as we drift off to sleep, we can take comfort in the knowledge that we are part of a grand cosmic story, one that is still unfolding in ways we can scarcely imagine. So let us dream of higher dimensions and hidden realms, of the mysteries that lie beyond the veil of our perception. Let us embrace the wonder and the awe that comes from contemplating the vastness of the universe and the strange and beautiful laws that govern its workings. And let us never lose sight of the fact that, even in our small corner of the cosmos, we have the power to shape our own destiny and to reach for the stars. Good night, and may your dreams be filled with the infinite possibilities of the dimensions beyond. As we continue our journey through the labyrinthine realms of higher dimensions, we find ourselves drawn to the pioneering work of a little-known German mathematician named Bernhard Riemann. In the mid-1800s, while his contemporaries were still grappling with the notion of four-dimensional space-time, Riemann was already exploring the uncharted territories of multi-dimensional geometry. Born in 1826 in a small village in the Kingdom of Hanover, Riemann showed an early aptitude for mathematics. As a young student at the University of Göttingen, he immersed himself in the abstract world of numbers and equations, often neglecting his physical health in favour of his studies. It was during this time that he began to develop the groundbreaking ideas that would later bear his name. In a seminal paper presented to the faculty in 1854, Riemann introduced the concept of n-dimensional manifolds, intricate mathematical spaces that could have any number of dimensions. These Riemannian manifolds, as they came to be known, provided a framework for understanding the geometry of higher dimensional spaces, paving the way for the revolutionary theories of relativity and quantum mechanics that would emerge in the early 20th century. But Riemann's contributions didn't stop there. He also developed the concept of Riemann surfaces, complex two-dimensional manifolds that allowed mathematicians to visualize the behavior of multi-valued functions. These elegant geometric constructs, which resemble sheets of paper glued together in intricate patterns, offered a new way of understanding the deep connections between algebra and geometry. Tragically, Riemann's life was cut short by tuberculosis in 1866, at the age of just 39, but his groundbreaking ideas lived on, inspiring generations of mathematicians and physicists to come. In the early 1900s, Albert Einstein would use Riemannian geometry as the foundation for his general theory of relativity, describing gravity as the curvature of four-dimensional spacetime. And in the latter half of the century, string theorists would build upon Riemann's insights to develop their visions of a universe woven from vibrating strands of energy, dancing in 10 or 11 dimensions. As we ponder these mind-bending concepts, it's easy to feel a sense of vertigo, as if the ground beneath our feet has suddenly given way to a dizzying abyss of infinite possibilities. But perhaps that's precisely the point. By stretching our minds to contemplate the strange and unfamiliar, we open ourselves up to new ways of seeing the world and new frontiers of knowledge waiting to be explored. And so, as we drift off to sleep, let us dream of the vast, untamed landscapes of higher dimensions, realms where the impossible becomes possible, and the boundaries of our imagination dissolve like mist in the morning sun. Who knows what wonders might await us there, in the uncharted territories of Riemann's manifolds and beyond? Perhaps we'll encounter strange fractal-like structures, their intricate patterns repeating endlessly at every scale. Or maybe we'll stumble upon vast hyperbolic vistas, where parallel lines diverge and the very notion of distance loses all meaning. We might even find ourselves wandering through the twisted, non-orientable surfaces of a Klein bottle or a Mobius strip, marvelling at the way they seem to defy the very laws of logic and reason. But whatever we encounter in these dreamscapes of the mind, one thing is certain: the journey itself is the true destination. For it is in the act of exploration, of pushing beyond the boundaries of the known and the familiar, that we truly come alive. And who knows? Perhaps someday, through the power of mathematics and the sheer force of human curiosity, we might even find a way to physically traverse these higher dimensions, opening up new realms of possibility for our species and our universe. Until then, we can take solace in the fact that the greatest adventures often begin in the most unlikely of places, in the quiet solitude of a mathematician's study, or in the hushed stillness of a darkened bedroom, as we drift off to sleep and let our minds roam free. So let us embrace the mystery and the wonder of it all, and see where our dreams might take us tonight. As we continue to explore the enigmatic world of higher dimensions, it's worth pausing to reflect on the sheer scope of the intellectual journey we've embarked upon. From the humble musings of ancient astronomers to the cutting-edge theories of modern physics, the quest to understand the nature of space and time has been a constant throughout human history. And yet, for all the progress we've made, there's still so much we don't know. Even the most advanced scientific theories of today, from string theory to loop quantum gravity, are ultimately just approximations. Best guesses at the true nature of reality, based on the limited data available to us. In a sense, we're like the proverbial blind men trying to describe an elephant, each feeling a different part of the beast and coming away with a different impression of the whole. But that's precisely what makes the pursuit of knowledge so exhilarating. The more we learn about the universe, the more we realize how much we have yet to discover. Each answered question seems to spawn a dozen new ones, each more intriguing than the last. And with every passing year, new technologies and techniques are opening up fresh avenues of inquiry, from the massive particle colliders probing the subatomic realm to the space telescopes peering deep into the cosmic void. Who knows what revelations the coming decades might bring? Perhaps we'll finally uncover the elusive theory of everything, a single elegant equation that encapsulates all the laws of nature. Or maybe we'll discover evidence of parallel universes, each with its own unique set of physical constants and dimensions. We might even find a way to harness the power of higher dimensions for practical purposes, like building wormholes or time machines. But even if we never achieve such lofty goals, the pursuit of knowledge is a worthy end in itself, for it is through the act of questioning, of striving to understand the world around us, that we give meaning and purpose to our lives, and in a universe that often seems cold and indifferent to our existence, that sense of purpose is a precious thing indeed. So let us continue to dream big and push boundaries of the unknown. Let us follow in the footsteps of visionaries like Riemann and Einstein, daring to imagine the impossible, and then working tirelessly to make it a reality. And most of all, let us never lose sight of the sense of wonder and awe that drew us to these cosmic mysteries in the first place. For in the end, the true beauty of science lies not in the answers it provides, but in the questions it inspires us to ask. And as long as there are curious minds willing to gaze up at the stars and ponder the nature of existence, the journey of discovery will never truly end. So dream on, dear listener, and may your curiosity never waver. The secrets of the universe are waiting to be unlocked, one dimension at a time. As we ponder the possibilities of higher dimensions, it's worth reflecting on how far our understanding has come. For most of human history, the concept of dimensions beyond length, width, and height was the stuff of pure imagination. But in the 19th and 20th centuries, a series of brilliant mathematicians and physicists began to seriously explore the idea that our universe might be woven from a higher dimensional fabric. One of the first to take up this challenge was Bernhard Riemann, a German mathematician who lived from 1826 to 1866. Riemann was a shy, sickly man who rarely lectured and published little in his lifetime. Yet his ideas would revolutionize geometry and lay the foundations for Einstein's general theory of relativity. In 1854, Riemann delivered a lecture that introduced the world to a new kind of geometry, one that went beyond the flat Euclidean space we learn about in school. Riemann envisioned curved spaces, where parallel lines could intersect or veer apart, and the shortest path between 2 points might be a curve, not a line. He realized that the geometry of a space depends on its curvature, and that this curvature could be described using mathematical objects called metrics. But Riemann didn't stop there. He proposed that the universe itself might be a curved higher dimensional space. In such a space, the familiar 3 dimensions of length, width, and height could be supplemented by extra dimensions, curled up too small for us to perceive. It was a daring idea, and one that would take decades to fully untangle. In the early 20th century, Albert Einstein built on Riemann's insights to create his general theory of relativity. Einstein realized that matter and energy warp the fabric of space-time, causing it to curve and bend. This curvature in turn determines the paths that objects and light take as they move through space. In Einstein's universe, gravity is not a force, but a consequence of the geometry of space-time. Einstein's theory was a triumph, but it left some deep questions unanswered. One of the most pressing was how to reconcile general relativity with quantum mechanics, the bizarre set of rules that govern the subatomic world. According to quantum theory, particles can be in multiple places at once, and can instantaneously influence each other across vast distances. These phenomena seem to defy the tidy deterministic picture painted by general relativity. In the 1920s, physicists Theodor Kaluza and Oskar Klein proposed a novel solution to this conundrum. Building on Riemann's ideas, they suggested that the universe might have an extra spatial dimension curled up into a tiny circle. If this extra dimension was small enough, it would be invisible to us, but its presence could explain some of the stranger features of quantum mechanics. The Kaluza-Klein theory was elegant, but it had a problem. If there was an extra dimension, why couldn't we see it? The answer, according to Klein, was that the extra dimension was curled up into a circle so small that it was beyond the reach of any possible experiment. It was a clever idea, but one that seemed untestable. Decades later, in the 1960s and 70s, physicists would return to the idea of extra dimensions with renewed vigour. Armed with powerful mathematical tools and a deeper understanding of the quantum world, they began to construct theories that envisioned a universe with not just one extra dimension, but many. One of the most promising of these theories was string theory. According to string theory, all the particles and forces that make up the universe arise from the vibrations of tiny, one-dimensional strings of energy. These strings are so small that they appear point-like at the scales we can probe with particle accelerators. But if we could zoom in far enough, we would see that they are actually extended objects, wriggling and oscillating in a higher dimensional space. The mathematics of string theory is fiendishly complex, but it has some remarkable properties. For one, it promises to unify all the forces of nature, including gravity, into a single, coherent framework. It also requires the existence of extra dimensions, typically 6 or 7 in addition to the 4 we know and love. But string theory has its share of challenges. For one, the extra dimensions it predicts are not the same as the single, curled-up dimension proposed by Kaluza and Klein. Instead, string theorists envision a universe in which the extra dimensions are compactified, curled up into intricate shapes called Calabi-Yau manifolds. These manifolds are mind-bendingly complex with hundreds of holes and interconnected passages. Another challenge for string theory is that it comes in not 1, but 5 different versions, each requiring a different number of extra dimensions. For years, physicists struggled to understand how these different theories could be reconciled. The answer came in the mid-1990s with the discovery of something called M-theory. M-theory is not really a single theory, but a network of theories that are all mathematically equivalent. It suggests that the 5 different versions of string theory are actually just different aspects of a single overarching framework, and it requires the existence of not just extra spatial dimensions, but an additional time dimension as well. The implications of M-theory are still being worked out, but it has already had a profound impact on our understanding of the universe. For one, it suggests that our 4-dimensional universe might be just one of countless brains, 3-dimensional membranes that float in a higher dimensional space. When 2 brains collide, the thinking goes, it could trigger a big bang, giving birth to a new universe. M-theory also raises the possibility that our universe is just one of an infinite number of parallel universes, each with its own unique set of physical laws. Some physicists have even suggested that these parallel universes could be connected by wormholes, tunnels through hyperspace that could allow for faster-than-light travel between different regions of the multiverse. Of course, these ideas are still highly speculative, and it may be decades or even centuries before we have the experimental evidence to support or refute them. But they offer a tantalizing glimpse of the strange and wonderful possibilities that await us in higher dimensions. As we lie here in the dark, our minds drifting off to sleep, it's worth reflecting on the incredible journey that has brought us to this point. From the musings of ancient astronomers to the mind-bending mathematics of modern physics, the quest to understand the nature of space and time has been one of the great intellectual adventures of our species. And who knows what new wonders await us in the years to come? Perhaps we will discover evidence of extra dimensions in the cosmic microwave background radiation, or detect the telltale signature of a parallel universe in the aftermath of a black hole collision. Or perhaps we will find that the universe is even stranger and more complex than we ever dared to imagine. But one thing is certain. The journey of discovery will continue, driven by the curiosity and creativity of scientists and dreamers around the world. And as we drift off to sleep, we can take comfort in the knowledge that we are part of that grand adventure, exploring the vast and mysterious cosmos one dream at a time. So let us embrace the possibilities of higher dimensions and all the strange and wonderful things they may contain. Let us be open to new ideas and new ways of thinking, even if they challenge our most cherished assumptions about the nature of reality. And let us never lose sight of the sense of wonder and awe that drives us to explore the unknown, to reach for the stars, and to dream of worlds beyond our own. Good night, and sweet dreams of the infinite possibilities that lie ahead. As we continue our journey through the mind-bending realms of extra dimensions, let us pause to appreciate the visionary thinkers who dared to imagine realities beyond the obvious. One such luminary was the Polish-Israeli physicist Oskar Klein, born in 1894. A prodigy from a young age, Klein excelled in his studies at the University of Stockholm, where he rubbed shoulders with the brilliant minds of the day, including Niels Bohr and Wolfgang Pauli. It was during a visit to Bohr's Institute in Copenhagen that Klein first encountered the ideas of Theodor Kaluza, a German mathematician who had proposed the existence of a fifth dimension to unify the forces of gravity and electromagnetism. Intrigued, Klein set out to refine Kaluza's theory, suggesting that the extra dimension might be curled up into a tiny circle, too small for humans to perceive directly. In Klein's vision, particles moving through the four familiar dimensions would also trace out circular paths in the fifth dimension, like tiny vibrating loops of string. The properties of these vibrations would give rise to the observable characteristics of mass and electric charge. It was a daring proposal, one that sought to bridge the gap between the infinitesimal world of quantum mechanics and the grand stage of Einstein's relativity. Though the Kaluza-Klein theory ultimately failed to unite the fundamental forces, it planted the seeds for later breakthroughs in theoretical physics. The concept of compact extra dimensions would resurface in string theory, which posits that all particles are actually different vibrational modes of impossibly small strands of energy, wriggling in a 10 or 11-dimensional arena. But the story of hidden dimensions is not just one of mathematical abstractions and ethereal realms. It is also a tale of human perseverance, of the unquenchable thirst for knowledge that drives us to probe the deepest mysteries of existence. Consider the life of Theodor Kaluza himself, a man who spent decades toiling in obscurity, his groundbreaking ideas largely ignored by the scientific community. Born in 1885 in what is now Poland, Kaluza showed an early aptitude for mathematics, earning his doctorate from the University of Königsberg at the age of just 24. But his academic career was hindered by the tumult of World War I and the economic hardships that followed. For years he struggled to secure a permanent position, supporting himself through tutoring and odd jobs. It was during this time of personal hardship that Kaluza began to ponder the problem of unifying gravity and electromagnetism. In a stroke of brilliance, he realized that adding a fifth dimension to Einstein's equations could elegantly merge the two forces into a single framework. Excited by his discovery, Kaluza sent his paper to Einstein in 1919, seeking the great man's approval. But Einstein was skeptical at first, and Kaluza's theory languished in obscurity for years. It wasn't until the 1920s, when Klein independently arrived at similar ideas, that the scientific community began to take notice. By then, Kaluza had finally secured a professorship at the University of Kiel, where he continued to teach and research until his retirement in 1935. Kaluza's story reminds us that the path to scientific enlightenment is often a lonely one, beset by doubts and setbacks. But it's also a testament to the enduring power of the human spirit, to our capacity for creativity and resilience in the face of adversity. In the annals of extra dimensions, Theodor Kaluza will always be remembered as a pioneer, a visionary who dared to think beyond the confines of the known world. And so, as we ponder the possibilities of unseen realms and hidden dimensions, let us also pay tribute to the human dimension of this grand cosmic quest. From the ancient astronomers who first charted the stars to the modern-day theorists probing the secrets of the subatomic world, each has played a part in expanding our understanding of the universe and our place within it. Who knows what revelations await us in the years and decades to come? Perhaps future generations will uncover evidence of extra dimensions, hidden in plain sight all along. Or perhaps the ultimate truth will prove even stranger and more wonderful than we can possibly imagine. Whatever the case, one thing is certain: the lure of the unknown will continue to beckon, drawing us ever onward in our search for meaning and transcendence. As we prepare to drift off into the realm of dreams, let us carry with us a sense of awe and wonder at the mysteries that surround us. In the vast expanse of the cosmos, in the intricate dance of subatomic particles, in the very fabric of space and time, there are secrets waiting to be unlocked, dimensions waiting to be explored. And though the journey may be long and the path uncertain, we can take comfort in the knowledge that we are part of a grand tradition, a lineage of seekers and dreamers who have dared to reach beyond the veil. So let us embrace the unknowable, the unfathomable, the infinite possibilities that lie hidden in the spaces between. Let us open our minds to the whispers of other worlds, other realities, other dimensions of being, and let us never lose sight of the essential human dimension of this cosmic quest. The courage, the curiosity, the irrepressible spirit of discovery that drives us ever forward, ever upward, ever outward into the vast and mysterious expanse of the universe. Good night, dear listeners, and may your dreams be filled with the wonders of dimensions unseen, waiting to be explored by the intrepid travellers of the mind. As we continue our journey through the dimensions, let us pause to appreciate the brilliance of the scientists who have illuminated this path. One such luminary was the Italian physicist Ettore Majorana, born in 1906. A prodigy from a young age, Majorana had a mind that seemed to operate on a different plane from his peers. His insights into the strange world of quantum mechanics were nothing short of revelatory. Majorana's most enduring contribution was his theory of the neutrino, a ghostly particle that can pass through solid matter like a phantom. In 1937, he proposed that the neutrino might be its own antiparticle, a mind-bending concept that physicists are still grappling with today. If proven true, the Majorana fermion could unlock secrets of the universe's origins and even pave the way for quantum computing in higher dimensions. But Majorana's story took a tragic turn. In 1938, at the age of 31, he mysteriously disappeared during a boat trip from Palermo to Naples. Some speculated that he had taken his own life, overwhelmed by the implications of his work. Others whispered that he had been recruited by a foreign government to build an atomic bomb. The truth remains unknown, adding to the mythic aura surrounding this brilliant and enigmatic figure. As we ponder Majorana's legacy, we can't help but wonder what secrets he took with him into the unknown. Perhaps, in some other dimension, he's still unravelling the mysteries of the cosmos, his genius unbound by the limitations of our earthly realm. From the haunting tale of Ettore Majorana, we turn to the mind-expanding ideas of Hugh Everett III. Born in 1930, Everett was an American physicist who proposed one of the most audacious and controversial theories in the history of science, the many-worlds interpretation of quantum mechanics. In the bizarre realm of the quantum, particles can exist in multiple states at once, a phenomenon known as superposition. But when we observe a particle, it suddenly snaps into a single state. This is known as wave function collapse, and it has puzzled physicists for decades. Why does observation seem to affect reality at the most fundamental level? Everett's radical answer was that it doesn't. Instead, he suggested that every quantum event creates a new universe, splitting reality into an infinite number of parallel worlds. In one world, the particle is spin up, in another, it's spin down. Both universes are equally real, but forever separated by the chasm of probability. If Everett is right, then there are versions of you living out every possible permutation of your life choices. A you who took that other job, married that other person, or never existed at all. It's a dizzying thought, one that challenges our very notions of identity and free will. But Everett's theory also opens up thrilling possibilities. Could there be ways to communicate or even travel between these parallel worlds? Might the key lie in those hypothetical extra dimensions curled up at the Planck scale? These are the sorts of questions that keep physicists up at night, dreaming of portals to the multiverse. Sadly, Everett struggled to gain acceptance for his ideas during his lifetime. Frustrated by the lack of recognition, he left academia and went to work for the defense industry. It wasn't until decades later that the many-worlds interpretation began to gain traction, as new generations of physicists grappled with the profound implications of quantum theory. Today, Everett's vision of infinite parallel universes has permeated popular culture, inspiring countless science fiction stories and fueling the imaginations of scientists and laypeople alike. As we drift off to sleep, we can't help but wonder, are there other versions of ourselves out there, dreaming these same dreams in worlds just beyond our reach? From the mind-bending realms of quantum physics, we turn our attention to the revolutionary ideas of a mathematician named Bernhard Riemann. Born in 1826 in the Kingdom of Hanover, Riemann possessed a rare genius for abstract thought. His visionary approach to geometry would lay the foundation for Einstein's theory of relativity, and forever change our understanding of space itself. In Riemann's time, geometry was still based on the ancient principles of Euclid. Euclid's geometry assumed that space was flat and extended infinitely in all directions. Parallel lines never intersected, and the angles of a triangle always added up to 180 degrees. These axioms had gone unchallenged for over 2,000 years, but Riemann dared to imagine a different kind of space. In his groundbreaking 1854 lecture on the hypotheses which lie at the basis of geometry, Riemann proposed that space could be curved. He envisioned a universe where parallel lines could meet, where triangles could have angles that sum to more or less than 180 degrees, and where the very fabric of space could warp and bend in response to the presence of matter and energy. Riemann's ideas were so far ahead of his time that many of his contemporaries struggled to grasp their significance. But Einstein, working over half a century later, would seize upon Riemann's curved space as the key to his theory of general relativity. In Einstein's equations, the force of gravity is not a mysterious tug between objects, but a natural consequence of the way mass and energy distort the geometry of space-time. Riemann's vision of a malleable, deformable space also opened up tantalizing possibilities for higher dimensions. In his Riemannian geometry, dimensions could be curved and finite, rather than flat and infinite. A two-dimensional being living on the surface of a sphere, for instance, would experience a curved space that loops back on itself, even though the sphere itself exists in 3 dimensions. This idea of curved, compact dimensions would later inspire physicists like Kaluza and Klein to propose extra spatial dimensions curled up at the Planck scale. If these dimensions exist, they could provide a unified description of gravity and electromagnetism, resolving one of the great outstanding problems in theoretical physics. As we contemplate Riemann's legacy, we marvel at the power of pure mathematics to reveal truths about the physical world. Riemann never lived to see the full impact of his ideas. He died of tuberculosis in 1866 at the age of 39, but his insights into the malleability of space and the possibility of higher dimensions continue to guide us as we explore the frontiers of science. In our mind's eye, we can picture Riemann in his study, his quill scratching across parchment as he ponders the mysteries of geometry. Outside his window, the world appears solid and unyielding, bound by the rigid laws of Euclidean space. But Riemann sees beyond this illusion to a universe of curved dimensions and infinite possibilities. As we drift off to sleep, let us dream of spaces unseen, where parallel lines converge and triangles dance to the curvature of the cosmos. As we continue our journey through the mind-bending world of dimensions, let us pause to appreciate the remarkable individuals who have shaped our understanding of these abstract realms. Their stories are woven into the very fabric of the cosmos they sought to comprehend. One such luminary was the German mathematician Bernhard Riemann. Born in 1826, Riemann grew up in a modest household, his father a pastor and his mother a homemaker. From a young age, Bernhard displayed an insatiable curiosity and a prodigious talent for mathematics. Legend has it that as a student, he mastered a 900-page textbook on number theory in just 6 days. Riemann's groundbreaking work laid the foundations for much of modern geometry and topology. In his famous 1854 lecture on the hypotheses which lie at the basis of geometry, he introduced the concept of Riemannian geometry, extending the notion of curved surfaces to higher dimensions. This revolutionary idea paved the way for Einstein's general relativity and the modern understanding of space-time as a malleable, dynamic entity. Tragically, Riemann's brilliance was cut short by tuberculosis. He passed away in 1866 at the age of 39, leaving behind a wealth of unfinished work and tantalizing conjectures. One of these, the Riemann hypothesis, remains one of the greatest unsolved problems in mathematics to this day. It stands as a testament to the enduring legacy of a man who dared to dream beyond the confines of ordinary space. As the 19th century gave way to the 20th, another visionary took up the mantle of exploring higher dimensions. The Swedish physicist Oskar Klein, born in 1894, is best known for his work on the Kaluza-Klein theory, which proposed the existence of a curled-up fifth dimension. Klein's journey to this groundbreaking idea was a circuitous one. As a young man, he studied under the great Niels Bohr in Copenhagen, absorbing the heady ideas of quantum mechanics that were revolutionizing physics. But it was a chance encounter with the work of Theodor Kaluza, a German mathematician, that set Klein on his path to extra dimensions. Kaluza had suggested that by adding a fifth spatial dimension to Einstein's equations, one could unify the forces of gravity and electromagnetism. Klein took this idea and ran with it, showing that if the extra dimension were curled up into a tiny circle, it could explain the quantization of electric charge. This was a profound insight, hinting at a deep connection between the very small and the very large. Though the Kaluza-Klein theory ultimately failed to unite all the forces of nature, it planted a seed that would sprout into the modern quest for a theory of everything. Klein's vision of a higher dimensional universe, with our familiar four dimensions accompanied by hidden, compact ones, would inspire generations of physicists to come. As we explore these hidden dimensions, we must also confront the limits of our own perception. Our brains evolved to navigate a three-dimensional world, and wrapping our minds around extra dimensions can be a daunting task. But as the pioneering mathematician Edwin Abbott showed, even a two-dimensional world can be rich with perplexing possibilities. In his beloved 1884 novella Flatland, Abbott imagined a universe consisting entirely of a flat plane. The inhabitants of this world, geometric shapes like squares and circles, could only perceive left and right, forward and backward. The notion of up and down was as alien to them as a fourth spatial dimension is to us. Through the eyes of a humble square, Abbott explored the mind-bending implications of life in fewer dimensions. The square's encounters with a sphere from the three-dimensional world, capable of feats that seemed miraculous to his planar perspective, served as a powerful metaphor for the limits of our own understanding. Flatland was more than just a mathematical curiosity. It was a sly commentary on the social hierarchies and prejudices of Victorian England. In Abbott's world, the more sides a shape had, the higher its status. Women, mere straight lines, were at the bottom of the pecking order. The satire was biting, but it also highlighted the ways in which our preconceptions can blind us to truths beyond our experience. As we ponder the possibility of dimensions beyond our own, Abbott's charming tale reminds us to approach these heady concepts with humility and an open mind. Just as the humble square struggled to comprehend the third dimension, we too may be flatlanders, groping in the dark for a reality that eludes our senses. And so, as we drift through the strange landscapes of higher dimensions, we find ourselves in good company. From the towering genius of Riemann to the maverick musings of Klein to the satirical vision of Abbott, the quest to understand the true nature of space and time has attracted some of the most brilliant and imaginative minds in history. Their stories remind us that science is, at its heart, a profoundly human endeavour. Behind every equation and every theory are the hopes, dreams and flashes of insight of individuals striving to make sense of the cosmos. In their struggles and their triumphs, we see reflections of our own yearning to comprehend the vast, mysterious tapestry of reality. As we continue to probe the secrets of higher dimensions, we stand on the shoulders of these giants. Their legacies light the way as we venture into realms that once seemed like pure fantasy. And while we may never fully grasp the true nature of the dimensions that lie beyond our own, the pursuit itself is a testament to the boundless creativity and curiosity of the human spirit. So let us dream of tesseracts and Calabi-Yau manifolds, of brains and bulk spaces. Let us ponder the possibility that our universe is but a slice of a higher dimensional reality, a cosmic page in an infinite book of wonders. And as we do, let us remember the visionaries who dared to imagine the unimaginable and who opened our eyes to the dizzying possibilities that lie beyond the veil of our everyday experience. Perhaps in some other dimension, Riemann and Klein are smiling down upon us, their equations etched into the very fabric of space-time. Perhaps Abbott's square is there too, marvelling at the strange and beautiful world he's awakened to. And perhaps, as we drift off to sleep, our minds will wander through these hidden realms, guided by the spirits of those who dared to dream of dimensions unseen. Good night, and may your dreams be as boundless as the cosmos itself. For in the end, the greatest gift of science may be the realization that we are all explorers, voyagers on an endless sea of wonder, forever seeking the shores of understanding. And as we sail on through the night, the stars above remind us of the myriad dimensions that may be, waiting to be discovered by the intrepid dreamers of tomorrow. The quest to understand the nature of dimensions has been a long and winding road, stretching back to the earliest days of human inquiry. In ancient Greece, philosophers like Aristotle and Plato grappled with the concept of dimensionality, seeking to understand the fundamental structure of the world around them. Aristotle, in particular, proposed that the universe was composed of 5 elements: earth, water, air, fire, and ether, each occupying its own distinct realm. This idea of separate dimensions for different types of matter would persist for centuries, influencing thinkers from the Islamic Golden Age to the Renaissance. But it was in the 17th century that the modern concept of dimensions truly began to take shape. The French philosopher and mathematician René Descartes, often called the father of analytic geometry, developed the Cartesian coordinate system that bears his name. By assigning numerical values to points in space, Descartes showed that geometric shapes could be described using algebraic equations. This revolutionary idea laid the foundation for the study of higher dimensions, as mathematicians realized that Descartes' system could be extended beyond the familiar 3 dimensions of length, width, and height. One of the first to explore this uncharted territory was the Swiss mathematician Leonhard Euler. In a series of groundbreaking papers published in the 1740s, Euler generalized the concept of dimension, showing that the principles of geometry could be applied to spaces of any number of dimensions. He introduced the idea of n-dimensional manifolds, geometric spaces that look locally like n-dimensional Euclidean space, even if their global structure is more complex. Euler's work opened up a new realm of mathematical possibility, paving the way for the study of hypercubes, hyperspheres, and other exotic higher dimensional objects. But it would take the genius of German mathematician Bernhard Riemann to truly revolutionize our understanding of dimensions. In his landmark 1854 lecture on the hypotheses which lie at the basis of geometry, Riemann proposed that the universe itself might be a curved higher dimensional manifold. This idea was a radical departure from the prevailing view of space as a flat 3-dimensional void. Riemann's insight would later prove crucial to Einstein's development of general relativity, which describes gravity as the curvature of 4-dimensional space-time. Einstein's theory, published in 1915, was a triumph of mathematical physics, but it also raised deep questions about the nature of dimensions. If space-time could curve and bend in the presence of mass and energy, what did that imply about the structure of the universe on the larger scales? Could there be additional dimensions beyond the 4 of space-time that we simply couldn't perceive? These questions would come to dominate theoretical physics in the decades that followed. In the 1920s, the German physicists Theodor Kaluza and Oskar Klein proposed a bold new theory that sought to unify Einstein's gravity with Maxwell's electromagnetism. The key to their approach was the addition of a 5th spatial dimension, curled up into a tiny circle at every point in space-time. In the Kaluza-Klein theory, the electromagnetic force arises from the geometry of this extra dimension, just as gravity emerges from the curvature of space-time in general relativity. While the theory ultimately failed to gain traction, it introduced the powerful idea that extra dimensions could help to unify the fundamental forces of nature. This concept would resurface in spectacular fashion in the 1970s and 80s, with the development of string theory. According to this ambitious framework, all particles and forces arise from the vibrations of tiny, one-dimensional strings of energy, wriggling and oscillating in a higher dimensional space. The mathematics of string theory is formidably complex, but it offers a tantalizing promise, a theory of everything that could unite all the known forces and particles into a single elegant framework. But string theory comes with a catch. In order for the math to work out, the universe must have not just 3 spatial dimensions, but 6 or 7 additional ones, curled up into complex shapes at every point in space. These extra dimensions are often described as a kind of Calabi-Yau manifold, named after the mathematicians Eugenio Calabi and Xingtung Yau, who first studied their properties. Calabi-Yau manifolds are incredibly intricate geometric objects, with a bewildering array of holes, loops, and other topological features. They are also exceedingly small, with dimensions comparable to the Planck length, the smallest possible unit of distance in quantum mechanics. The possibility of such tiny hidden dimensions has captivated the imaginations of scientists and science fiction writers alike. In the popular novel Flatland, published in the 1884 by Edwin Abbott Abbott, the inhabitants of a two-dimensional world are visited by a mysterious sphere from the third dimension, who tries to explain the nature of higher dimensional space. The book has become a classic of mathematical fiction, using the device of dimensions to explore questions of perception, belief, and social hierarchy. More recently, the idea of extra dimensions has made its way into mainstream science fiction, from the tesseracts of Madeleine L'Engle's A Wrinkle in Time to the mind-bending bulk of the movie Interstellar. These stories tap into the deep human fascination with the unknown and the unexplored, inviting us to imagine realities beyond the confines of our everyday experience. But the search for extra dimensions is more than just a flight of fancy. In recent years, physicists have proposed a number of experimental tests that could potentially detect the presence of hidden dimensions. These include precision measurements of gravity at short distances, searches for microscopic black holes at particle colliders, and observations of the cosmic microwave background radiation left over from the Big Bang. One of the most exciting possibilities is that extra dimensions could provide a solution to one of the deepest mysteries in modern physics: the nature of dark matter. This invisible substance, which makes up roughly 85% of the matter in the universe, has so far eluded all attempts at direct detection. But some theories suggest that dark matter could be made up of particles that propagate through extra dimensions, interacting only weakly with the familiar matter of our three-dimensional world. Another intriguing idea is that extra dimensions could be the key to understanding the arrow of time. In our everyday experience, time seems to flow inexorably, from the past to the future, with a clear distinction between cause and effect. But at the microscopic level, the laws of physics are symmetric with respect to time reversal. They work equally well running backwards or forwards. Some physicists have speculated that the arrow of time could arise from the geometry of extra dimensions, with the flow of time emerging as a kind of holographic projection from a timeless higher dimensional reality. As we ponder these mind-bending possibilities, it's worth remembering that our understanding of dimensions is still very much a work in progress. The mathematics of higher dimensional spaces is complex and often counterintuitive, and experimental evidence for extra dimensions remains elusive. But the quest to unravel the secrets of the universe is one of the great intellectual adventures of our time, and the study of dimensions is a crucial part of that journey. Perhaps one day, far in the future, we will discover that our familiar three-dimensional world is just a shadow of a vaster, higher dimensional reality. Or perhaps we will find that the dimensions we know are all there is, and that the beauty and complexity of the universe emerge from the intricate dance of matter and energy in the space-time we call home. Either way, the exploration of dimensions will continue to stretch our minds and fuel our imaginations as we seek to understand our place in the grand tapestry of the cosmos. As we drift off to sleep, let us dream of the countless possible worlds that may exist in the higher dimensions beyond our ken. Let us imagine the strange and beautiful geometries that could be woven into the fabric of space and time, and the incredible discoveries that await us as we continue to push the boundaries of human knowledge. And let us take comfort in the fact that, no matter how vast and complex the universe may be, we are all a part of its intricate and eternal dance. As we continue our exploration of the mind-bending possibilities of extra dimensions, let's turn our attention to some of the visionary thinkers who have dared to venture beyond the boundaries of our perceived reality. One such pioneer was the brilliant mathematician and physicist Hermann Minkowski. Born in 1864 in what is now Lithuania, Minkowski showed an early aptitude for mathematics, earning his doctorate at the age of 21. He went on to teach at several prestigious universities in Germany and Switzerland, making significant contributions to the fields of geometry and number theory. But it was Minkowski's work on the mathematical foundations of space-time that would cement his place in history. In 1907, he gave a groundbreaking lecture in which he proposed that space and time should be viewed not as separate entities, but as a single, unified, four-dimensional continuum. This revolutionary idea laid the groundwork for Einstein's theory of special relativity, which would forever change our understanding of the universe. Minkowski's space-time was a strange and beautiful place, where the familiar concepts of past, present, and future blurred together into a seamless whole. In this four-dimensional world, the path of an object through space and time could be described by a single curve, known as its world line. And just as a two-dimensional being could not comprehend the up and down of our three-dimensional reality, Minkowski suggested that we three-dimensional creatures might be equally blind to the true nature of the four-dimensional space-time in which we are embedded. Despite the groundbreaking nature of his work, Minkowski himself did not live to see the full impact of his ideas. He died suddenly in 1909, at the age of 44, from a ruptured appendix. But his legacy would live on through the work of his students and collaborators, including a young Albert Einstein, who would go on to revolutionize our understanding of gravity and the very fabric of the universe. As we ponder the life and work of Hermann Minkowski, it's hard not to feel a sense of awe at the power of the human mind to transcend the limitations of our everyday experience. Through the language of mathematics, Minkowski and others like him have given us a glimpse of a reality beyond our senses, a reality in which the very nature of space and time is called into question. And yet, even as we marvel at these intellectual achievements, we must also recognize the humbling truth that our understanding of the universe is still far from complete. The mysteries of extra dimensions, of the true nature of space and time, continue to elude us, tantalizing us with their promise of a deeper, more fundamental reality. Perhaps as we drift off to sleep, we can take comfort in the knowledge that even the greatest minds of our species have grappled with these same questions, these same yearnings to understand our place in the grand cosmic scheme. And who knows? Perhaps in the realm of dreams, unfettered by the constraints of our waking world, we might catch a glimpse of those hidden dimensions, those unseen vistas that lie just beyond the edge of our perception. Let us dream, then, of a universe stranger and more wonderful than we can possibly imagine. Let us dream of a reality in which the very fabric of space and time is ours to explore, to unravel, to marvel at in all its infinite complexity. And let us hold fast to the hope that someday, through the tireless efforts of scientists and thinkers like Hermann Minkowski, we may yet come to understand the true nature of the cosmos in which we find ourselves. But for now, let us simply surrender to the gentle embrace of sleep, secure in the knowledge that the universe will still be there waiting for us when we awake, ready to be explored anew with fresh eyes and a sense of wonder that never grows old. Good night, dear listener, and may your dreams be filled with the beauty and mystery of the cosmos. As we continue to ponder the strange and wonderful possibilities of extra dimensions, it's worth taking a moment to reflect on the incredible leaps of imagination and intellect that have brought us to this point. One of the most remarkable minds to grapple with these questions was the great physicist and mathematician Paul Dirac. Born in 1902 in Bristol, England, Dirac showed an early aptitude for mathematics and science, earning a degree in electrical engineering from the University of Bristol, before going on to pursue graduate studies at Cambridge. It was at Cambridge that Dirac would make his most enduring contributions to the field of physics. In the late 1920s, he developed a mathematical framework that united the seemingly incompatible theories of quantum mechanics and special relativity. This work, known as the Dirac equation, predicted the existence of antimatter, a discovery that would later be confirmed experimentally and would earn Dirac the Nobel Prize in Physics in 1933. But Dirac's interests were not limited to the realm of subatomic particles. He was also fascinated by the idea of extra dimensions, and in the 1930s he began to explore the possibility that our universe might be embedded in a higher dimensional space. In a paper published in 1938, Dirac proposed a model of the universe in which our familiar three spatial dimensions were supplemented by a fourth, curled-up dimension that was too small to be detected by our current instruments. This extra dimension, he suggested, might be the key to unifying the forces of nature and resolving some of the deepest mysteries of physics. Dirac's ideas about extra dimensions would later be taken up and expanded upon by other physicists, including the great theorist Abdus Salam, who shared the Nobel Prize with Stephen Weinberg and Sheldon Glashow in 1979 for their work on the electro-weak interaction. Salam was particularly intrigued by the idea that the universe might have as many as 11 dimensions, with 7 of them curled up into a tiny compact space. As we reflect on the contributions of thinkers like Dirac and Salam, it's hard not to be struck by the sheer audacity of their ideas. The notion that our universe might be just a small slice of a much larger, higher dimensional reality is one that challenges our most basic intuitions about the nature of space and time. And yet, as strange and counterintuitive as these ideas might seem, they are grounded in the rigorous language of mathematics and the painstaking work of experimental physics. Through the efforts of scientists like Dirac and Salam, we have been given a tantalizing glimpse of a reality that lies beyond the bounds of our everyday experience. As we drift off to sleep, perhaps we can take comfort in the knowledge that even the most abstract and esoteric realms of science are ultimately grounded in the same sense of wonder and curiosity that drives us to explore the world around us. And who knows, perhaps in the depths of our dreams, we might catch a glimpse of those hidden dimensions, those unseen vistas that have captivated the minds of great thinkers for generations. So let us dream, then, of a universe filled with strange and marvellous possibilities. Let us dream of curved spaces and extra dimensions, of antimatter and electro-weak interactions, and let us hold fast to the hope that someday, through the tireless efforts of scientists like Paul Dirac and Abdus Salam, we may yet come to understand the true nature of the cosmos in which we find ourselves. But for now, let us simply surrender to the sweet embrace of sleep, secure in the knowledge that the mysteries of the universe will still be there waiting for us when we awake. Good night, dear listener, and may your dreams be filled with the beauty and wonder of the cosmos. As we continue to explore the strange and fascinating world of extra dimensions, it's worth taking a moment to consider some of the most recent developments in this field. Developments that are pushing the boundaries of our understanding and challenging our most basic assumptions about the nature of reality. One of the most exciting of these developments is the idea of the holographic principle, first proposed by physicist Gerard 't Hooft in the early 1990s, and later expanded upon by theorists like Leonard Susskind and Juan Maldacena. The holographic principle suggests that our three-dimensional universe might actually be a projection of information encoded on a two-dimensional surface, much like a hologram. To understand how this might work, imagine a cube in three-dimensional space. Now imagine slicing that cube in half and looking at the cross-section. What you would see is a two-dimensional square, filled with an intricate pattern of lines and shapes that encode the information about the original three-dimensional cube. According to the holographic principle, our entire universe might be like that cube, with all of its complexity and richness encoded on a distant two-dimensional boundary. This idea is rooted in the mathematics of string theory and the physics of black holes, which suggest that the amount of information that can be contained within a region of space is proportional not to its volume, but to the area of its boundary. If true, the holographic principle would have profound implications for our understanding of space, time, and the nature of reality itself. It would mean that the three-dimensional world we perceive is actually a kind of illusion, a projection of a deeper, more fundamental reality that lies beyond our reach. But the holographic principle is just one of many strange and mind-bending ideas that have emerged from the study of extra dimensions in recent years. Another is the notion of brain worlds, the idea that our universe might be just one of many three-dimensional brains floating in a higher dimensional space, like sheets of paper stacked in a book. According to this idea, the reason we don't perceive these extra dimensions is that we're confined to our own particular brain, much like characters in a two-dimensional cartoon world. But just as those cartoon characters might be able to detect the presence of other sheets of paper in the stack, we might be able to detect the presence of other brain worlds through subtle gravitational effects or other indirect means. These ideas are still highly speculative, and much work remains to be done to test them experimentally and mathematically. But they offer a tantalizing glimpse of a reality that is far stranger and more wonderful than anything we could have imagined just a few decades ago. As we ponder these mind-bending concepts, it's hard not to feel a sense of awe and humility at the sheer scale and complexity of the cosmos. We are but tiny specks in an unimaginably vast and intricate tapestry, a tapestry woven from the very fabric of space and time itself. And yet, through the power of our minds and the tools of science, we are slowly but surely unravelling the secrets of that tapestry, teasing out the hidden patterns and structures that underlie the reality we perceive. It is a grand and noble quest, one that has occupied some of the greatest thinkers in human history. So let us continue to dream and to wonder, to explore and to question. Let us follow in the footsteps of those great minds who have gone before us, who have dared to venture beyond the boundaries of the known and to imagine the unimaginable. And let us never lose sight of the profound beauty and mystery that surrounds us, even in the deepest, darkest reaches of the cosmos. Good night, dear listener, and may your dreams be filled with the infinite possibilities of the universe. For in the end, it is only through the power of our imagination that we can hope to grasp the true nature of reality in all its strange and wondrous glory. As we ponder the possibilities of hidden dimensions, it's worth reflecting on the great minds who brought us to this point. One such luminary was the German mathematician Bernhard Riemann. Born in 1826, Riemann's revolutionary ideas would lay the groundwork for Einstein's theories and the modern conception of space-time. Riemann grew up in the Kingdom of Hanover, in what is now Germany. The son of a Lutheran pastor, he was a shy and sickly child who found solace in mathematics. At the age of 19, he went to study at the renowned University of Göttingen, where his brilliance quickly caught the attention of his professors. In 1854, Riemann delivered a lecture that would change mathematics forever. In just 8 pages, he introduced the concept of Riemannian geometry, a way of describing curved spaces in any number of dimensions. Riemann proposed that space itself could be curved, with its geometry determined by the matter and energy within it. This was a radical departure from the flat Euclidean geometry that had held sway for over 2,000 years. Riemann's insights were so far ahead of his time that even he struggled to grasp their full implications. He wrote, "It remains quite undecided whether the assumptions on which the geometry rests might not be proven false by the observations, however distant that prospect seems at present." Little did Riemann know that within his lifetime, astronomers would observe the first hints of curved space. In 1919, during a solar eclipse, Sir Arthur Eddington measured the bending of starlight around the Sun, confirming Einstein's prediction from general relativity. Einstein later wrote, "The magic of this theory will hardly fail to impose itself on anybody who has truly understood it. It represents a genuine triumph of the method of absolute differential calculus, founded by Gauss, Riemann, Christoffel, Ricci, and Levi-Civita." Riemann's geometry paved the way for the concept of space-time as a malleable fabric, warped by the presence of mass and energy. It opened the door to such mind-bending ideas as black holes, wormholes, and the expanding universe, and it provided the mathematical language to describe extra dimensions, whether curled up at the quantum scale or extending into realms we can scarcely imagine. Sadly, Riemann struggled with ill health throughout his life. He died of tuberculosis in 1866 at the age of just 39. On his deathbed, he was working on a hypothesis about the distribution of prime numbers, a conjecture that remains unproven to this day, and one of the great unsolved problems in mathematics. Though his time was short, Riemann's legacy endures. His ideas continue to inspire and challenge mathematicians, physicists, and anyone who dares to dream of dimensions beyond our own. As we drift off to sleep, we can take comfort in the knowledge that the story of human discovery is still unfolding, guided by the brilliant lights of thinkers like Bernhard Riemann. And yet, even as we celebrate these great minds, we must acknowledge that our understanding of the cosmos is far from complete. The more we learn, the more questions arise, beckoning us onward to new frontiers. One of the most tantalizing mysteries in modern physics is the nature of dark matter and dark energy. These invisible substances are thought to make up over 95% of the universe, yet we have no idea what they are. Could they be related to extra dimensions, as some theories suggest? Dark matter was first proposed in the 1930s by Swiss astronomer Fritz Zwicky. He noticed that galaxies in the Coma cluster were moving much faster than could be explained by the visible matter alone. There had to be some unseen mass providing extra gravitational pull. Later observations of galactic rotation curves confirmed that most galaxies are held together by a halo of dark matter, outweighing the ordinary matter by a factor of 5 to 1. Dark energy, meanwhile, was discovered in the late 1990s, when two teams of astronomers found that the expansion of the universe is accelerating. This came as a complete surprise, since the gravitational pull of matter should be slowing the expansion down. To account for the acceleration, there must be some mysterious force pushing the universe apart, counteracting the inward pull of gravity. The leading explanation for dark energy is that it's a property of empty space itself, a cosmological constant that provides a constant tiny push on every cubic centimetre of the universe. This idea actually originated with Einstein, who introduced it into his equations to achieve a static universe. He later called it his greatest blunder, but the discovery of cosmic acceleration brought it back in a big way. So what do dark matter and dark energy have to do with extra dimensions? Some physicists believe that these mysterious substances could be leaking in from higher dimensional realms. For example, in theories with brain worlds, three-dimensional membranes floating in a higher dimensional bulk, gravity is the only force that can leak off our brain into the bulk. This could explain why gravity is so much weaker than the other forces, and potentially provide new avenues for dark matter detection. Other theories, like the dark fluid model, propose that dark matter and dark energy are actually two faces of a single, higher dimensional substance. This fluid would have negative pressure, allowing it to act like dark energy on large scales while clumping like dark matter on smaller ones. The model is still speculative, but it provides an intriguing link between these twin cosmic mysteries. As we ponder these ideas, we may feel a sense of vertigo, our minds stretching to comprehend realms beyond our everyday experience. But we can take solace in the fact that even the greatest thinkers of history grappled with similar feelings of awe and uncertainty. When Einstein first encountered Riemann's geometry, he struggled to wrap his mind around it. In a letter to a friend, he wrote, "I have been occupying myself exclusively with the problem of gravitation, and now believe that I will overcome all difficulties with the help of a mathematician friend. But one thing is certain, never before in my life have I toiled as much, and I have gained enormous respect for mathematics, whose more subtle parts I considered until now, in my ignorance, as pure luxury." Like Einstein, we may toil to grasp the subtleties of higher dimensions and cosmic mysteries, but in the struggle lies the joy of discovery, the thrill of pushing the boundaries of human knowledge, and as we drift off to sleep, we can dream of the wonders yet to come, the secrets waiting to be unlocked by curious minds in dimensions yet unseen. Perhaps one day, far in the future, our descendants will have tamed gravity, harnessed the power of dark energy, and learned to navigate the higher dimensions with ease. They may look back on our era with a mix of amusement and admiration, marvelling at how we groped our way to understanding with the limited tools at our disposal. Until then, we continue the grand human tradition of gazing up at the stars and dreaming of what lies beyond. We stand on the shoulders of giants like Riemann and Einstein, peering into the darkness with eyes wide open, ready to embrace whatever wonders the cosmos has in store. So let us rest now, our minds filled with visions of tesseracts and brain worlds, secure in the knowledge that the story of science is far from over. The dimensions may be hidden, but they are not lost. And as long as there are curious souls willing to venture into the unknown, the journey of discovery will never end. Good night, brave explorers of the cosmos. May your dreams be as boundless as the dimensions you seek. As we ponder the possibilities of extra dimensions, it's worth taking a moment to appreciate the incredible progress we've made in understanding the universe. Just a few centuries ago, the idea of other worlds beyond our own was the stuff of myth and speculation. Today, we have mathematical frameworks and physical theories that allow us to explore the cosmos in ways our ancestors could scarcely imagine. One of the most fascinating aspects of this journey has been the realization that our perception of reality is fundamentally limited. We experience the world through our senses, which are attuned to just a narrow slice of the electromagnetic spectrum. Our brains construct a coherent picture from this input, but it's far from a complete representation of what's out there. Consider, for example, the humble flatworm. With no eyes or ears, it navigates its 2D world by sensing chemical gradients and vibrations. To a flatworm, the concept of a third dimension is utterly alien. And yet, we know that flatworms are embedded in a 3D universe, even if they can't perceive it directly. In much the same way, We may be embedded in a higher dimensional reality that we can only glimpse through the lens of mathematics and indirect experimentation. It's a humbling thought, but also an exciting one. Who knows what wonders await us as we continue to push the boundaries of our understanding? Of course, the road to discovery is rarely smooth. Throughout history, great scientists have faced opposition and ridicule for daring to challenge the status quo. Galileo spent the last years of his life under house arrest for advocating a heliocentric model of the solar system. Einstein's theories were dismissed as Jewish physics by some in the scientific establishment. And today, researchers pursuing ideas like string theory and supersymmetry are often accused of engaging in untestable speculation. But as the great physicist Richard Feynman once said, the imagination of nature is far, far greater than the imagination of man. Just because an idea seems strange or counterintuitive doesn't mean it's wrong, and even if a theory turns out to be incorrect, the process of exploring it can lead to valuable insights and new avenues of investigation. Take the case of Theodor Kaluza, the German mathematician who first proposed the idea of extra-spatial dimensions in the 1920s. Kaluza was attempting to unify Einstein's theory of gravity with Maxwell's equations of electromagnetism, and he found that he could do so by adding a fifth dimension to spacetime. Although Kaluza's original theory was ultimately abandoned, it laid the groundwork for much of the subsequent research into extra dimensions. In the 1970s and 80s, physicists began to explore the possibility that the extra dimensions required by Kaluza-Klein theory and string theory might be curled up at incredibly small scales, too tiny for us to detect directly. This idea of compactified dimensions has since become a mainstay of theoretical physics, and it has led to some truly mind-bending possibilities. In some models, our universe is just one of countless brains floating in a higher dimensional space called the bulk. In others, the Big Bang that gave birth to our cosmos was simply the result of two brains colliding in the bulk. These ideas may sound like science fiction, but they're grounded in rigorous mathematics and physical principles. And while we don't yet have any direct evidence for extra dimensions, there are tantalizing hints that they might be real. For example, some theories predict that extra dimensions could manifest as tiny deviations in the strength of gravity at very small scales. Experiments using ultra-precise torsion balances and microscopic resonators are currently searching for these deviations, and could potentially provide the first concrete evidence of dimensions beyond our own. Other researchers are looking for signs of extra dimensions in the behavior of subatomic particles. The Large Hadron Collider at CERN, for instance, is searching for evidence of Kaluza-Klein particles, heavy cousins of ordinary particles that could only exist if extra dimensions are real. So far, these experiments haven't turned up anything conclusive, but they've already helped to narrow down the possible shapes and sizes of extra dimensions. And as our technology improves, we may finally be able to probe the hidden recesses of the cosmos and uncover the truth about the nature of space-time. Of course, even if we do find evidence of extra dimensions, there's no guarantee that we'll ever be able to perceive them directly. Just as a flatworm can't visualize a cube, our brains may simply not be wired to process higher dimensional information. But that doesn't mean we can't appreciate the beauty and complexity of the universe on a deep, intuitive level. Whether we're marveling at the intricate patterns of a snowflake or contemplating the vast expanse of the night sky, we're all capable of experiencing a sense of wonder and awe at the mysteries of the cosmos. And who knows? As we continue to explore the frontiers of science and mathematics, we may one day develop new ways of thinking and perceiving that allow us to glimpse the true nature of reality. We may find that the universe is even stranger and more wonderful than we ever dared to imagine. But for now, as we drift off to sleep, let us take comfort in the knowledge that we are part of an incredible cosmic story, a story that has been unfolding for billions of years and will continue to unfold long after we're gone. And let us dream of the day when we finally unlock the secrets of the dimensions and take our rightful place among the stars. Thank you for joining me on this journey through the strange and fascinating world of extra dimensions. If you enjoyed this exploration, please like and subscribe for more soothing yet educational bedtime stories. Until next time, may your dreams be filled with the infinite possibilities of the cosmos. Good night.